idea of the multipole expansion right at the start. I said, here's how we can express the potential as the sum of these spherical harmonics and radial functions, right? And what I am doing now is actually just justifying that a little bit better to you. I'm going to do this anyway for an arbitrary distribution of charge. What does the potential look like? And then show you that that n expansion comes out of this, and that's what we're going to call multipole expansion. So if I have just some distribution of charge in here, that's not a chicken.
No, it's a chicken nugget.
Stop making me hungry.
That's charge density in the prime coordinate systems. dV prime. That's what the potential looks like. If I actually know the charge distribution, then I just can do that numerically. I can't even solve it in closed form, but I should be able to do it. And now I'll write down what we actually did a moment ago when we used the law of cosines. But between any position and any particular primed position, it's r squared plus r prime squared minus 2r prime cos theta prime.
Square root.
What?
Square root. Law of cosines is that square. That works too.
Thank you. R squared times 1 plus just pulling out the factor of r squared. And for far outside the distribution, r prime over r is much, much less than 1, right? So that I could write r prime minus r minus r prime is approximately equal to square root of 1 minus epsilon, where epsilon is small. Actually, this is true. I just haven't defined for you what epsilon is yet, so I'm okay. But epsilon is small in both cases. R prime over r and r prime over r squared are both going to be small. So this is true no matter what, right? But I'm going to be considering the situation where that is small. And epsilon, in that case, including all the terms, is r prime over r times 1 minus, oops, times r prime over r minus 2 cos theta prime. Again, prime telling us that we're integrating over the charge itself. So that means that I can expand the potential, because the potential is going to go as 1 over r. Right? 1 over r minus r prime, rather. I can expand it in epsilon. So I can write that 1 over r minus r prime is equal to 1 over r times 1 plus epsilon half. Right? That's, I'm doing something pretty simple. Pretty simple there. But I could rewrite that as 1 over r times 1 minus 1/2 epsilon plus 3/8 epsilon squared minus 5/16 epsilon cubed.
Excuse me, Professor.
And so on. Yes.
Should there be an R in front of that square root of 1 minus epsilon?
Yes. Don't you see it? Huh.
Oh, it's right there. It's so obvious.
Or writing it out in terms of the angles that we're actually going to see. It's 1 over r times 1 minus r prime over r cos theta prime plus r prime over r squared times 3 cos squared theta minus 1. Just taking, I'm collecting orders here, all right? So I've got all these epsilons, and remember epsilon is equal to r prime over r times r prime over r minus 2 cos theta, all right? What I'm going to do is collect orders in r prime over r. I'm just collecting the terms together. I wrote that out, I expanded it first, assuming that epsilon was small. Then once I expanded it, I wrote it all out again and collected orders in R. Okay? Minus R prime over R cubed times 5 cos cubed theta prime minus 3 cos theta prime over 2 plus other terms. But guess what? Those, if you look at them, are Legendre polynomials. So this looks like 1 over r, the sum L equals 1 to infinity of r prime over r to the L, p sub L of cos theta. So 1 over r itself, 1 over r minus r prime itself, ends up looking like an expansion, or a series, not an expansion, sorry, a series in Legendre polynomials. Okay? That means that I could take advantage, coming back here, of the orthogonality properties of Legendre polynomials, multiply both sides by a Legendre polynomial and the weighting factor, and integrate, and I will find the coefficients of that series that give rise to this potential. All right. So now I'm going to write the result again. So this is what I started this segment on. Now I'm going to finish this segment on the result. The arithmetic that I just did here, which had to do with using first law of cosines, large distance compared to the size of the distribution that I'm looking at. So r prime is always small compared to r, right? And the angles are always not, the angles are always small, and the distance r prime over r is small. So then I could expand the potential. I could expand 1 over r. Once I've done that expansion, I rewrite and I find out that it gives me Legendre polynomials. That's
For all epsilon.
a really hand-waving argument, plausibility argument, for why I can write down what I'm about to write down. But I haven't given you the entire argument, and I'm not going to. I'm just going to wave my hands. Okay. So having said that,
Waving on video.
This is
have to stick around because this is going to be the definitions that you need for the homework. So phi of r is equal to 4 pi sum over L and M, appropriate sums, 1 over 2L plus 1, Q sub L M y L M theta phi over R to the L plus 1, where Q sub L M, the coefficients, are found using orthogonality conditions. Are the integral y L M theta prime phi prime, so that's where the charge is, R prime of L rho of R prime dV prime. And this thing here, this coefficient, is called the multipole moment. And if we actually work it out for a distribution, we find out that Q00 is 1 over the square root of 4 pi times the net charge in the distribution. Q10 is the dipole moment of the distribution in the z direction. Q20 is 1/2 square root of 5 over 4 pi. And now I have one more definition that I have to give you. Q33, which is what's called the quadrupole moment. Quadrupole moment. Maybe I gave you this definition in homework. In Cartesian coordinates is the integral 3xi, that's like the x, y, z direction, so I'm using a component notation here. Xj minus r prime squared delta ij rho that. I can write the first 3 orders then of the description of the charge distribution. The net charge, the dipole moment in each of 3 directions. Okay, so I've got px, py, pz in each of 3 directions, and the quadrupole moment, which tells me how 4 charges that are paired with one another, so the net charge is 0, are ordered in space. Okay? This allows me to find all of those things that describe the charge distribution. Okay, so that's what you're going to solve for some quadrupole moments for homework. Okay, thank you.
And cut.